Thank you very much for the introduction, and thank you for having me here. And thank you to the audience for waking up bright and early on the last day of the workshop. So today I'm going to talk about light matter interaction in a slightly different platform as what we've been hearing all week. We still have photons, but these photons are slightly different. They're microwave photons, and they don't travel, they don't fly. They're stationary modes. Okay, so I am from Singapore, as the city looks very different from where we are now. But we just like what we're seeing here and elsewhere in Europe, we have a very active academic scene and a large quantum science and technology center called the Center for Quantum Technologies. We're about 15 years old, 200 plus researchers. We have a very competitive and very well supported PhD program as well. So if you're interested, please take a look at our website. There are about 20 different research groups on various topics. So my teams is one of the fairly more recent additions in the center. So we started with COVID, or COVID started with us. In December, I started in April 2020, and with some COVID-induced delays, we managed to set up the lab around December that year. And 5 years on, this is us still kind of having fun together, and the team has grown. And our main focus in the past few years have primarily been using bosonic CQED systems to play with the light and matter interaction and tease out interesting physics and interesting applications from them. Okay, so I keep talking about bosonic CQED. What are they? They're essentially a very versatile engineered electrical system that allows us to understand the interaction of microwave photons and artificial atoms. So we don't have real atoms, we engineer them out of electrical circuits. And the main building blocks are LC oscillators in this case, in our case. This is conceptually very simple. You have inductor and a capacitor, and they give you a harmonic oscillator. Right? You have a well-defined mode frequency, and you have transition energies. So it just gives you the standard potential and equidistance transitions. Um, so just on this own, we can build this kind of LC oscillators in various shapes and forms. You probably have seen in news announcements of circuit QED devices with oscillators of maybe this shape or planar or in a rectangular shape. So this is it does not change the physics. It's just a choice, engineering choice of what role we want the resonator or the cavities to play. For the rest of my talk, I'll stick to devices that have this kind of shape. It's a 3D cylindrical device where we essentially machine out the shape here, leaving the stub in the middle. And this defines our electromagnetic mode that confines the microwave photons so we can interact with it. But just on its own, it's not super interesting. It's an oscillator, it's linear. We can't selectively address any of the levels. We drive them all of them at the same frequency. So we have to introduce some sort of control knob to make this more interesting. And our chosen, or the most common one, are the transmount type of devices. But there's no reason that it has to be. The key thing is it has to be somewhat nonlinear of a desired form. So for the key elements that we're looking at here, the nonlinear part is the Josephson junction. And the Josephson junction is very convenient for this because essentially it is just a nonlinear inductor. You can fabricate it in a way that it has a chosen nonlinear inductance. So you can, engineer this. It's not defined by certain atomic transitions or limited by nature. So this is all very tailored kind of spectrums that we can make. So if you have something nonlinear in the simplest form, say a transmount, where it's just one Josephson junction with a capacitor, then you can have anharmonicity or nonlinearity in the system, and you can now selectively pick out one or two or three levels to address because they're spectrally separated. Right. So for transmounts, they typically look something like this, where we print or we lithographically define features on substrates such as sapphire or silicon, and we make these large film patterns for the capacitive element, and then we use the tunnel junctions. So these are the superconducting, insulating, superconducting layers that forms the Josephson junction. So this technology is fairly mature now. It's been used in many quantum processor initiatives, and there's for good reasons, because It's a very simple nonlinear element. It's tailored. You can design it for your specific applications, and the fabrication is not too stringent, let's say. These are really the key building blocks we play with, and we put them together in various different ways. But perhaps before I move on to talk about bosonic elements, I think let me just really mention the fact that circuit QD probably is at the moment most recognized for building processors, near-term processors that has maybe have hundreds of qubits at this point. Some preliminary works on quantum error correction. So I don't know if the audience here cares about this or not, but I think I find it quite curious that announcements like this strangely correlates with dramatic increases in stock prices in quantum computing companies these days. So maybe that's one reason to listen to news on these things. But for me, what really speaks to my heart is the other element in our hardware platform. It's the LC oscillator. And in this LC oscillator, we have a good harmonic oscillator, which is usually manifested as a 3D high Q cavity. And then, oh, the animation didn't work. Then we introduce a nonlinear control element to allow us to go from different points in phase space, both in a linear and nonlinear way. Okay, so in this very simple module that looks somewhat like this, we have now a bosonic mode. We have nonlinear interactions that we can engineer through transmon type of ancillary elements. And then we also can extract information from the harmonic oscillator by mapping certain properties onto the qubit, onto the transmon, and then just read it out through another linear mode. Okay, so in more circuit language, this looks something like this in the simplest configuration, where we have one linear mode that we designate as the memory or the cavity, the long-lived bosonic element. Then we have a nonlinear element that mediates certain couplings that goes beyond Gaussian operations, and then we can introduce another linear mode for readout and information extraction. Okay, so this is something like this is quite easy to engineer at this stage. So you can just build things of nuts and bolts and chosen materials. So usually high purity aluminum to make the cavities, and then standard fabrication for the nonlinear device on chip, and the planar resonators for readout. Right. So from the top view, it will look like this, where you have this cavity looking down, and then the nonlinear element there. So just to put some orders of magnitude, these couplings typically are in the order on the order of megahertz, right? So that's quite convenient. So it gives us pretty strong nonlinear control. And beyond that, we do not only control the coupling or design the coupling between different elements. We also put a lot of effort in designing and controlling the couplings to the environment. What that means is we now have different lifetimes that we can play with, so different scales, time scales as well. So the element that we want to use as a storage cavity, we want it to be long-lived, so we engineer it to be extremely weakly coupled to the environment. So this is really a stationary mode. It does not leak out through the transmission lines. So you can't do homodyne directly anymore or detecting the field leaking out. But because of this coupling to the ancillary elements, you can still measure its properties fairly efficiently. Then the transmon is something that we want to control quickly. So we typically allow it to couple to the environment a little more strongly, limiting its lifetime typically to hundreds of microseconds. And then finally, the readout is really the element that allows us to get information out of the whole system. So we couple very strongly to a transmission line that goes to the electronics. So that brings us to maybe hundreds of nanoseconds in terms of coherence or lifetimes, right? So we have lots of knobs to play, both on the time scales as well as the coupling strengths. So that's pretty convenient. Now, maybe to now translate this language to a more familiar picture for the audience here, this is essentially just light matter interaction in maybe cavity QED or in all the AMO systems, where you have a light field confined in a cavity and you have an atom that's nonlinear that you can select transitions of, right? So you can already think about different regimes where this may happen. This could be interesting. So for instance, if we make this G over delta, which is the physical coupling over the delta is the detuning between modes, then if you make that really small, close to zero, so that means there's very little coupling between the atom, the light, and the matter, then there is essentially no interaction. They don't care about the existence of one another. And that's sometimes useful because if you want to build a memory, you don't want it to be affected by the presence of atoms around it, right? Bosonic memory. So this is quite good. Also in processes where you have long idling periods where you don't want parasitic processes to be constantly taking place. We can move along this line, maybe to the other extreme end, where you can make them resonant with each other. And that's also a useful regime because now you can do resonant control. You can load photons from one mode to another, have vacuum Rabi type of interactions to create non-trivial states in the light field. And we like this as well. It allows mapping of information, exchange of energy, etc. Now, for circuit QED, we're typically somewhere in between. Okay, and this is what we usually call the dispersive regime, which is essentially just James Cummings Hamiltonian. You take the limit where G is smaller than delta, you take the higher order terms, and now we get to a fairly simple Hamiltonian, where now what you have is there's no more direct exchange of energy, but the presence of one mode or the presence of excitation of one mode affects the frequency of the other mode, right? This is symmetric on both the electron and the matter. And this is convenient, this state dependent frequency shift, because now we have a way to both map information in this spectral way, as well as to perform nonlinear controls on the microwave field or the light in our picture. And this is really the key operating regimes of circuit QED. So maybe in a slightly different way to look at this is we have this full landscape where we have G and delta are both normalized by the characteristic decay times of the system. And then we typically operate in this range where G over delta is smaller than 1, but perhaps not many orders of magnitude smaller. Right? And in this regime, we like the operations because we have nonlinear control, so we can have number resolved regimes where the chi, so the this dispersive shift, is on the order of megahertz. So that gives us direct control just by spectral selectivity. We can also tune that to be slightly smaller, but still that gives this non-negligible dispersive shift, which allows us to play with it in terms of conditional displacement operations, right? So spectrally, it just looks like this, where if you have this shift, what you can think of is the mode of the resonator. Now, the frequency of the resonator depends on the state of the qubit, right? And then the frequency of the qubit depends on the number of photons you have in the resonator. And the wise sort of strong or weak or resolve or not resolve, it just depends on how wide this is and how far separated they are in frequency, right? So this is all relative to some coherence timescales. Now, using this, we can create cat states, which are one of the very popular candidates for a lot of applications. So I think you've heard a lot of different ways of creating non-Gaussian states in optical or AMO systems. So for us, because we have this native dispersive coupling, we have a slightly easier time of doing so. So I'm just giving two examples here. One is called the arbitrary phase gate that's number dependent, where essentially you create a coherent states, then selectively put some phases on certain photon number states, and then create another displacement or coherent state with a well-chosen phase, such that you have interference effects taking place, allowing to keep only the wanted Fock state numbers or cat state, several Fock state numbers, whilst interfering away the rest unwanted ones. Right? So this is pretty handy. Another way that we can do this is actually go fully go to numerics fully, where we just use a gradient based approach and give it a state, let it do a state transfer for us using the native Hamiltonian. And this is also pretty convenient because you can create really any state you want in the microwave cavities with good fidelity. And a typical example is something like this, where we can't make sense of the pulse anymore, but you can see that for in this instance, we want to create a Fock state 6 here. It starts from vacuum and it goes to 6 very, very nicely, although we don't know what's going on in the middle. Right, so I guess the short message here is really there's a lot of tools that we can play with because of this dispersive coupling that we have. Now, what can we do with these nice tools and our hardware? Well, there are lots of options. We can use them to study quantum foundations, interference effects, entanglements, etc. We can use them for quantum computing applications. There are lots of research groups and companies working on this. You've heard about GKP code yesterday, CAD codes, etc. And we can also use them to look into maybe more tailored applications such as quantum metrology, quantum simulation. In this talk, I will just show one example where we did a quantum metrology kind of measurement in our system, right? So again, building on what we talked about of cat states, what we did is to look into its fundamental features in phase space and think about how that might benefit us in terms of being able to sensitively detect certain information. So if we just take a look at the Wigner function and try to get some intuition, we can see that the blobs in a Wigner function of a cat details the population, how large the coherent state superpositions are. And the fringes in the middle, they tell us how coherent your quantum superposition is, right? And you can see that the oscillations are pretty fast. And the larger the cat, the faster they get. And when you have fast oscillations, this is usually kind of giving you a hint that it's sensitive to something, right? You can already think if I shift that fringe a little bit, I'm seeing a large difference between my initial and final state. Um, so that's exactly where what inspired us. We know that this feature, these oscillations are fast, and if we have movements in phase space, either rotations or displacements, then we're going to see a rapid reduction in overlap. So this work was done in my team last year and published this year in PRX Quantum in collaboration with Radim and Kim Min, where we draw on this inspiration and really think about if we have a rotation in this case, what would happen to this overlap between the initial pre-rotated state and the state after the rotation in phase space. And turns out this is actually something that gives us extremely high Fisher information even at a smallish cat state. Right, so this is maybe slightly different from, it's just a it's just displaced cat, so very much the same properties as a regular cat state. So how we did this in circuit QED, bosonic CQED, is essentially using the native operations that I've been talking about. So we start with a state transfer process where we prepare our coherent state superposition, so a displaced cat, and then we impart some phase on it to mimic the rotation that we want to sense. And then essentially we do perform another pulse to transfer it back to attempt to transfer it back to the original state, and then we measure how much is back to vacuum, right? So effectively, the this operation plus this optimized measurement gives us the information of how much overlap I have between my initial and final state. And you can imagine the more the rotation is, the smaller the overlap is, right? And this is the raw data from our measurement. And you can see that as you increase the rotation, the overlap drops dramatically. And for the we've heard about how to extract Fisher information from this kind of measurements many times now. So that's very handy for me to just quickly go to the result, where we essentially extract the Fisher information and plot it over the different angles we've performed the rotations for. And we see that for our quantum state, we get a much higher Fisher information compared to the classical, semi-classical counterpart, which is just a coherent state. And this is done with real experimental imperfections, raw data, no post-processing or errors. They're done with the same number of shots, same length of gate sequences, etc. So it's a very fair comparison. Then based on this, we can also extract the gain that we can achieve as a function of how large our cat is, right? So you can imagine if you have a really tiny cat, then you don't have a lot of fringes, this will not work too well. So ideally, you want to go to really large cats. But if we want to do this on real hardware, the larger the cat, the more prone it is to decoherence and unwanted coherent errors. So we don't want to go too high. So what we saw, which is very encouraging, is that even at a very small, so square root of 3, relatively small size of cat that people can essentially make easily in any bosonic CQD hardware these days, we have a significant quantum enhancement in the sensitivity, right? So we get about 7.5 dB in this rotation sensing. Even at a very small cat. And this in simulation, we know if we go further, we can get much more. But of course, that it starts to remove some of the nice practicality that we can gain with this simple implementation. Now, what makes this even better or even more in an on-demand way is that we can optimize based on the practical limitations without touching the hardware or changing the scheme. So with Radim's team, we figured out that if you have certain constraints, essentially what you want to do is just to optimize the weights of the two coherent state superpositions, and this even a little bit of non-Gaussianity would give you a quantum enhancement. So for a specific use case where we impose a limit on the average photon numbers, we want to keep on average the energy of the state low. We see that by tweaking just these weights, we can find very optimal points where we can get the highest visual information with that constraint in mind. And again, this is just programming the pulses, and there's no hardware changes required. The same protocol as well. So it really is very versatile. I think very practical from a point of view of maybe actually building a device out of it and perform this purpose robustly. Okay, so that's very nice. I think we learned a lot through this. There's some follow-up theory work in Radim's work on just understanding the role of non-Gaussianity in this. And there's also a follow-up experiment in our team on going to multi-parameter estimation using similar intuitions we've developed here. But before I end, let me just draw you back to this little landscape I showed you earlier, right? So I mentioned that we typically operate in this regime where we're safely in the well-known dispersive area. But in the beginning of the talk, I also hinted or alluded to the fact that both the decoupled or the resonantly coupled regimes are also useful for different purposes. So ideally, right, we don't want to limit it. We don't want to be limited to a specific operating point. But as you could see, this is nuts and bolts. I can't really change it after. It's all solid state. It's not like I can just change laser. I guess move the atom out or something. So what we want to do is to be able to then still keep all the nice properties of the long lifetime, of the simple controllability, while allowing us to have access perhaps to a wider range of dynamics in a single experiment. Right. So what we did, so this is highly non-trivial. We actually took a lot of iterations from different groups, and the way we approach this is to think about tuning the frequency of our nonlinear mode relative to our oscillator mode, right? And the reason is because this is a much more easily tunable element, and by tuning delta, so we couldn't tune G easily. So if we tune delta, we can then still stretch it across the different regimes. So what we did is introducing flux tunability in a clever way that does not kill the coherence times of our long-lived cavity mode. Okay, so we introduced this via magnetic hose. It's essentially many layers interleaved with superconductors and ferromagnetic materials. So the superconductors the ferromagnetic material allows the field to propagate in, while the superconductor forbids it from fanning out. So it goes directionally to the qubit and where we want it to go. But not just this, we need to make sure the coil, the source of the magnetic field, is small so it can be tuned quickly. We also need to make sure there's appropriate filtering so that our nice cavity mode does not leak out through this lossy element, which consists of non-superconducting materials. Right. So overall, we can get this is a typo here. Hundreds of microseconds, close millisecond lifetimes. We can tune over one or two flux quanta. We can also get bandwidth of hundreds of megahertz. So these are pretty handy, right? And what we did to test this is to really see in a single experiment if we can move across this entire dynamical interaction regimes. So the test we came up with is to first go to the resonant regime, where we get vacuum Rabi interactions between the transmon and the cavity, and that allows us to make Fock states very quickly. So our G here is tens of megahertz, so we can make a Fock state in tens of nanoseconds. And then we tune it away to a more safely dispersive regime to perform our standard Wigner tomography. And you can see that we can create good Fox days 1 and 2 and others as well, and we can do good Wigner tomography in this manner. Another test we did is then we tune it even further away in a very weakly dispersive regime. And then there is more convenient to measure the characteristic function instead of Wigner function, purely due to the sort of the different native gates that we can more easily have access to. And with that, we can also get evidence of good tomography. And of course, the same state preparation is still has as high quality. right? So this, in a single experiment, now it really shows you the power of introducing this tunability, where in the beginning you tune it to be fully resonant, and then within a single experiment, within tens of nanoseconds, you tune it to be very, very weakly dispersively coupled to allow tomography in our standard, using our standard toolbox. Okay, so let me just wrap up over here. So in this talk, I introduced the bosonic CQD platform as a really sort of versatile playground for understanding or playing with light matter interaction. I've shown you two instances of the work that we've done in the team, one on parameter estimation using the interference fringes of the cat, and the other one on introducing flux tunability while preserving coherences in our hardware. But this is not the only things we've done in the past few years. We've been busy playing also with measurements in bosonic CQD, making it more efficient, making it more robust against the noise in the system. We also looked into perhaps engineering some error resilience of the cats, which we use for all sorts of different interesting applications in quantum optics. Right. So going forward, we'll continue to build along this theme. We have several projects that's ongoing right now in terms of engineering interactions between two or three bosonic modes, engineering dissipation and Hamiltonian dynamics, etc. So we want to keep the system small, so not really into scaling personally, but we think there's still a lot of rich physics we can study even with a smallish device. Okay, and just to end, we're a very diverse team. I think it's pretty fun to work on this with people from not just different backgrounds, but all those different with different skill sets. We have engineers, material scientists, CS people, physicists, etc. And if you're interested in this kind of small experiments, please reach out to me. You can find our website or write to me directly over email. Okay, thank you very much.
Thank you. Thank you, Yvonne. Questions?
Yeah, thank you for the nice talk. It's impressive work, especially the small cats for the rotational sensing. So I was wondering, like, what will be the main limiting factors for the sensing's performance? For example, is it like loss rate of the cavity or preparation, etc.? So could you
Right.
comment on
Yeah,
that?
that's a good question. So, for what we did, the main limitations are the higher order effects in the system. So, for instance, I told you we can couple the nonlinear element to a harmonic oscillator, but with this coupling, the oscillator is not truly a harmonic oscillator anymore. It inherits a little bit of the nonlinearity. So this higher order term kicks in at larger and larger cats, and it's also more prone to photon loss. So in general, it's there are ways to correct for some of this, but in a way, like it's convenient to not have to worry about it and keep the performance at a good level without going too far in photon number.
So do you also like integrate like other Kerr cancellation mechanisms, or just keeping the end limited
Yeah,
bevel?
in
Ah,
this particular implementation, we're not actively canceling
mhm.
anything, but yeah, that's some of the mitigation methods one could use. Yeah.
Okay, there.
Thank you for the talk. The regarding the application of this sensing, like can it be used, and how feasible is it to apply to a usual like qubit measurement scheme, where normally coherent state is used for heterodyne detection or something? But can you replace it with this cascade, display cascade? Yeah.
Um, Not really, no, because here we're doing a series of operations on the on the harmonic oscillator, and if you flip the roles of this, then this actually becomes overly complex for just reading out the qubit state. Is not necessary. Just the standard dispersive readout offers you much better performance, much quicker.
Oh, I see. Thank you.
Thank you. If there is no further question, let's thank
Thank you very
the
much.
speaker again.